Assalamu alaikum wa rahmatullah. Today, inshallah, we're going to solve Cambridge exam, October-November 2022, paper 61. Let's start it. Question 1. Sulfur dioxide gas is toxic, denser than air, and it is also soluble in water. Sulfur dioxide gas can be made by adding dilute hydrochloric acid to solid sodium sulfite and heating the mixture. The gas made can be dried by passing it through concentrated sulfuric acid because the concentrated sulfuric acid is a drying agent. Here we have a diagram to the apparatus used to dry and collect some of sulfur dioxide gas. There are two errors in the way the apparatus has been set up. Here, as we can see from the diagram, hydrochloric acid is added to the flask through a pipette. Then the gas formed is passed through concentrated sulfuric acid for drying and then collected into inverted gas jar. Indicate with an arrow on the diagram where the heat should be applied. Here is the flask containing the reaction mixture where hydrochloric acid is added, so there is an arrow to show the position of heat directly below the reaction mixture flask. Give the name to the item labeled A. A is a conical flask. Give the name to the substance labeled B. B is the solid sodium sulfite. Suggest why in this experiment it should be carried out in a fume cupboard. It is mentioned here in the beginning of the question that sulfur dioxide gas is toxic. It is a very toxic gas to the respiratory system and can cause suffocation. So the answer will be sulfur dioxide gas is toxic gas. Identify two errors in the way the apparatus has been set up. Number 1, the gas jar should not be inverted. Here it is mentioned in the beginning of the question that sulfur dioxide gas is denser than air, so it should not be collected in an inverted gas jar because it will be escape from the gas jar because it's denser than air. So the first error, the gas jar should not be inverted. The second error, the tube linking the flask should go into sulfuric acid. This one, the tube that links the two flasks together, should go into sulfuric acid for the gas to be dried using sulfuric acid. And the tube, the second one, this one, that goes from the sulfuric acid to the gas jar should not touch sulfuric acid. So the position of these two tubes should be reversed. This is the second error. The tube linking the flask should go into sulfuric acid, or we can say the tube from the flask to the gas jar should not touch sulfuric acid. We can write either of them or both of them. Question 2. Student investigate how the solubility of sodium sulfate in water changes with the changing temperature. 8 experiments were done. First, experiment 1. First, we will get the mass of the empty evaporating basin. Then we will add excess sodium sulfate in a beaker with 100 centimeter cube of cold water. We will mix the water with the sodium sulfate and heat until the temperature reaches 15. Some of the sodium sulfate has dissolved to form saturated solution. So we have saturated solution in the beaker, contain 100 centimeter cube of water. We will take 25 centimeter portion of the saturated solution and we will put it in the evaporating basin and heat it until no more steam could be seen, and the sodium sulfate remained in the evaporating basin. We will determine the mass of the evaporating basin and the solid sodium sulfate remaining. Then we will repeat the experiment at a higher temperature than experiment 1. This will be experiment 2, and another experiment 3 with the higher temperature than 2, and so on until reach to experiment 8 with the higher temperature than experiment 7. Here we will complete the table showing the thermometer reading and calculating the mass of the sodium sulfate remaining in the evaporating basin at each temperature. Here in the first column, we will take the reading from each thermometer. The first experiment was 15, then 22, 29, 32, 34, 46, 61, and finally 84. Then here we have the mass of the empty evaporating basin and the mass of the basin plus sodium sulfate. So we will subtract the second one, this one, minus the mass of the empty basin to get the mass of the sodium sulfate remaining. Continue subtracting to contain the mass of sodium sulfate: 3.9, 5.9, 9.6, 11.7, 12.3, 11.7, 11.2, and finally 10.8. Here we will plot our results from experiment 1 to experiment 8 on the grid. We will draw two curves of best fit, one through the first 4 points and one through the second 4 points. Extend the two curves so they can cross. So here I have the first 4 points and the blue line, and the second blue line we have another 4 points. I draw a best fit line for the first 4 points and then a second best fit, and they cross together in this point, as we can see. From your graph, deduce the mass of the solid sodium sulfate that remains in the evaporating basin if the mixture in the beaker is heated to 55. So we will go to the temperature, determine the point 55, and we will draw a line upward until meet the line to determine the mass of sodium sulfate remaining, which will be 11.3. This will be the mass remaining at 55. You have to show your work on the graph. So the mass of the solid sodium sulfate remaining will be 11.3. The mass of the sodium sulfate remaining that you determined in the previous question, which was 11.3, is the mass of sodium sulfate that will dissolve in 25 centimeter cube of solution at 55 degrees Celsius. Use your answer to calculate the concentration in gram per decimeter cube of saturated aqueous sodium sulfate at 55. 1 decimeter equal to 1000 centimeter cube. This mass, which is 11.3 gram, is the mass of the sodium sulfate that present in 25 centimeter cube. So we will determine the mass in grams that is present in 1000 centimeter cube, which is equal to 1 centimeter. Here, by cross multiplication, we can find that the mass of sodium sulfate present in 1000 centimeter cube or 1 decimeter cube will be 452 gram per decimeter. The student repeat the experiment and find that 11 gram of solid sodium sulfate remained in the evaporating basin. So 11 gram remaining, and he wants you to use your graph to deduce two possible temperatures at which the mixture in the beaker may have been heated. So we will return back to the graph, determine the mass, which is 11 gram, exactly 11 gram. We will draw a line to intersect both lines, the blue lines. The first intersection will be here and the second one will be here. So we will determine these two temperatures by going down to the x-axis. The first one is 31 and the second one is 67. These are the two temperatures that the solution might be heated to reach to final mass of 11 gram. So we will go back to the question, write 31 and 67. These are the two possible temperature to which the mixture in the beaker may have been heated. Name the item of the apparatus that can be used to remove 25 centimeter cube portion of the saturated solution from the beaker. Here we want to remove exactly 25 centimeter cube, so we will use pipette because it is very accurate. Suggest why it is important that an excess sodium sulfate is added to the water in the beaker to make sure of the formation of saturated solution. Because we want to prepare saturated solution, we have to add excess sodium sulfate. Suggest why the mixture in the beaker was stirred as it is heated to speed up dissolving. So we will stir it until all the sodium sulfate dissolved quickly. The saturated solution was heated until no more steam could be seen and the solid sodium sulfate remained in the evaporating basin. So remember that we took 25 centimeter cube portion from the beaker and put it in evaporating basin, heated until no more steam could be seen to remove all the water and determine the mass of the solid sodium sulfate. Suggest a better way of ensuring that all the water has been evaporated. To ensure that all the water has been evaporated, we should reheat and reweigh until obtain a constant mass. That's ensure that no more water to be evaporated. Use your graph in B to deduce what would be observed if the saturated solution of sodium sulfate at 80 degrees Celsius is cooled until 50. So we will go back to our results and our curve. From 80, the solution will be cooled from 80 to 50. As we can see here, at the temperature 80, we have 10.8 grams of sodium sulfate, and at the temperature 50, we have about 11.2 grams. From 11.2 to 11.7, 50 will be here in the middle. So there will be no change, no observation from cooling from 80 degrees to 50 degrees. No sodium sulfate will be precipitated, so no observation, and the answer will be no change. Or the solution remain colorless because no sodium sulfate will precipitate by cooling. The solution is still saturated at 50 degrees Celsius. Question 3. Two substances, solid W and solid X, were analyzed. Solid W was zinc bromide. We will start with tests on solid W, complete the expected observation. First, solid W was dissolved in water to form solution W, and the solution is divided into 3 equal portions. The first portion of the solution, we add aqueous ammonia, then dropwise, then in excess. When we add aqueous ammonia, we should expect that we will have a precipitate of zinc hydroxide, white. The observation will be white precipitate, and it will dissolve in excess ammonia. The second portion, we will add 1 centimeter cube of dilute nitric acid, followed by few drops of aqueous barium nitrate. Barium nitrate is used to test for sulfate, and here we don't have sulfate ions, we have zinc bromide, so the answer will be no change. To the third portion, we will add 1 centimeter cube of dilute nitric acid, followed by few drops of aqueous silver nitrate. And silver nitrate is the reagent used to test for halide ions, and it will react here because we have zinc bromide, we have the precipitate form, it will be silver bromide. It's a creamy precipitate. The observation will be creamy precipitate. Of course, the equation is not required, just wrote it for illustration. Test on solid X. 1 gram of solid X was placed in a boiling tube and it is heated strongly. Then a strip of filter paper soaked in acidified aqueous potassium manganate was held at the mouth of the boiling tube. Heating strongly means we have a decomposition reaction. So by decomposition, we have something formed and we test it with potassium manganate. The acidified aqueous potassium manganate turns from purple to colorless. The remaining solid X was dissolved in water to form solution, and the solution is divided into 3 equal portions. To the first, we will take 1 centimeter cube of dilute nitric acid added, and a few drops of aqueous silver nitrate were added to the first portion. No change, that means we don't have halide ion. Another test, dilute nitric acid added and few drops of aqueous barium nitrate to the second portion. We will have a white precipitate that indicates the presence of sulfate ion. Test number 4, aqueous sodium hydroxide was added dropwise and then in excess to the third portion. A green precipitate formed and remain in excess that indicate the presence of iron 2 ions, and the green precipitate will be the iron 2 hydroxide. Name the gas given off in the test number 1. Here we test the gas formed with potassium manganate and the color changed from purple to colors. This is the test of sulfur dioxide gas. So the gas formed is sulfur dioxide. Heating the sulfate iron 2 sulfate strongly decompose it into to form sulfur dioxide gas. So the gas tested in test 1 is sulfur dioxide. Water vapor is also given off in test 1. Give a chemical test for water and the expected observation if the water is present. So we want to test the presence of water. We can use anhydrous cobalt chloride. It is blue in color. The anhydrous cobalt chloride is blue. The observation that indicate the presence of water, that the blue color change into pink. The color of the anhydrous cobalt chloride change from blue to pink. Identify solid X, as we said that solid X is iron 2 sulfate. Question 4. The writing experiment or investigation. The leaves of some trees containing colored substance which can be used as pH indicator. These colored substances are soluble in ethanol but insoluble in water. You should assume that nothing else in the leaf is soluble in ethanol. Plan an investigation to extract the colored substance from the leaves and test to see if they are can be work as a pH indicator. You are provided with the leaves from the tree and the common laboratory apparatus and chemicals. So we have to first extract the colored substance from the leaf, then test to see if it works as pH indicator. So step number 1 is grind the leaves using mortar and pestle, then add ethanol because the colored substance is soluble in ethanol. So we will add ethanol to the grinded leaves and stir it well. Filter the mixture and get the filtrate, then divide the filtrate into 2 portions. To the first portion we will add hydrochloric acid, and to the second portion we will add sodium hydroxide. Then we will look for the color change in each portion. If it is a pH indicator, it will give different color in the acid than it will give in the alkali. Here we come to the end of our exam. Comment down below if you have any question. Like the video and subscribe to the channel to receive all the updates. Thank you for watching. Wish you all best of luck.